pleasure to introduce you to Dr. Leigh Orf. He's going to give a past histories communication and give a pretty awesome talk. I think you're going to really enjoy it. Dr. Orf received his Bachelor of Science degree at UW-Madison in 1989 and received his PhD under John Anderson in 1997. Following a short postdoc, he was faculty at UNC Asheville from 2000 to 2003 and faculty at Central Michigan University from 2003 to 2015. In 2015, Leigh returned to UW-Madison as a research scientist where he works at the Cooperative Institute for Meteorological Applied Studies. There's two different SIMs, and I get
this
them
is
confused.
UW Sims, not OU Sims, right?
So he's interested in understanding the inner workings of thunderstorms, such as how downbursts and tornadoes form, and the specific threats these damaging storms present to the natural and built environment. Thank you, Leigh, for coming, and take it away.
All right, well, thanks, Dan, and thank you so much for your hospitality, Dan, and carting me around and stuff. He's a good guy. He's been running around like a crazy man. If dim lights are good for some of this stuff, we'll bring out more of the details.
Lower some of these blinds?
Maybe close lower the blinds. I don't want everyone to slant them. Slant them. That'll be good enough. It'll help some of the detail come out of some of the images. So while people are doing that, again, I'd like to say I appreciate being invited. This is a privilege to come and talk to you all. I've really enjoyed talking to faculty and students, grads and undergrads about their research. I'm learning a lot about what goes on here that I didn't know, which is always good. I've been mostly familiar with Dan and Robin's work for reasons that are probably obvious since they study supercells as well. So today, let me introduce the problem here. The problem that I'm trying to tackle involves why tornadoes form in supercells sometimes and not other times. And once in a great while, supercells kick out these just incredibly nasty, devastating tornadoes. You can't just look on radar, see a supercell, and call a tornado warning. So we do know a fair amount about what pre-storm environmental conditions such as CAPE and shear. We have a whole suite of parameters we look at in the pre-storm environment to try to give us an idea what kind of storm might form, what convective mode might come about. But when it comes down to actually accurately forecasting whether a supercell is going to produce, like, say, a top-end tornado, because those are the ones that do the vast majority of the damage and devastation, we essentially have very little skill. I would posit that we have actually a lot of new knowledge to be found in how supercells work. Some of the work I'm doing by running models at very high resolution, when you run at 30, 10, 15 meter resolution, you start to pick out features that just don't come out in lower resolved simulations. And I think there's energy at these scales that are very important that you really need to run at high resolution to capture. Not all things require this, but some things do. Certainly, I think we don't understand why or what the balance of force is going on in a supercell that's producing like an EF5 tornado on the ground for an hour. I'm going to sort of jump straight ahead to my sort of conclusion slide or my hypothesis, and I don't normally do this, but I wanted to sort of set the stage for what I'm about to spend the rest of my talk talking about. This is based upon my work with, it's highly biased against the 24 May 2011 storm I've been simulating for a while. So this was a storm that produced a long track EF5 tornado. It's not the May 31st, 2013 storm, but it's similar location, a different storm. I have been simulating storms at high resolution for a while, and I've come to the conclusion that tornadogenesis is actually a storm-wide process. Its origin is in the strengthening of a low-level mesocyclone via the ingestion of primarily streamlined vorticity that originates from within the cold pool, primarily along the forward flank. Now, if that sentence is gobbledygook, I hope that most of my rest of my talk isn't. It's a lot of weathery terms, but essentially, I think that you need to get the updraft to be super strong to support a long tornado, and essentially there's things going on in the forward flank of the storm where the storm is going. It's creating all this rain, hail, and evaporation and cooling. It produces this cold pool that's just full of swarming with vorticity and all sorts of stuff, and then it's ingesting it back into itself. In one simulation I'll talk about, it seems like tornadogenesis occurs almost as an afterthought or an artifact. There's this steady increase in the strengthening of the mesocyclone. The updraft is getting strong near the ground, but tornado seems to form from a conglomeration of vorticity that's kind of hanging out already. There's plenty of vorticity, vertical vorticity in supercells that you don't always see in your eye, but there's little vortices almost everywhere. And there's radar studies of this. People have seen this before. I mean, people have set up clear air, go out to a field and just set up detectors just to do clear air turbulence, and you see vortices, vortices, vortices. Vortices are everywhere. There's been a sort of a theoretical barrier, I think, to our understanding of tornadogenesis, and that we're always assuming there's no vertical vorticity unless a downdraft nearby brings it to the ground. And what I'm saying is there's downdrafts all through supercells. They're doing what they have to do, but you don't need one proximate to create vertical vorticity because it's being advected in from other parts of the storm, partly. So if my theory is correct, I need to figure out how this, a feature we've discovered that is in a bundle of the streamwise vorticity, what we call the streamwise vorticity current, and or the SVC, is that playing a key role here in helping to lower the pressure, which is helping to strengthen the updraft, which is helping to do the stretching, which is helping to maintain and form a tornado. I don't see genesis and maintenance as two different things. I see them as the same process just continuing. It's not like the tornado is hard to explain, but I'll just continue on here. So hopefully I'll at least prove that I'm not too crazy in my assumptions based on here. So the approach I'm taking, I'm a guy who comes at this from the perspective of give me the biggest supercomputer in the world that I can get access to and let me play with it for a while to answer questions about the environment that cannot be answered in another way. So in other words, I'm only interested in doing, at least in the context of supercells, super high resolution work. That's like my baseline. So the coarsest resolutions simulations I do these days are about 30-meter grid spacing. And that's a grid spacing where you can start to resolve a tornado pretty well. Literally, you don't have to call it a tornado-like vortex anymore. But I would say that the smaller vortices, the ones that help to feed the tornado and create it, are just marginally resolved. This is not for everyone, okay? Many of us are passionate about the weather and going out and observing it and seeing it. I like computers. I love programming. I discovered this a long time ago, long after I discovered I loved weather and science and everything else. So when I discovered as an undergrad and getting into grad school that you can take these two skills together and do some cool stuff, I'm like, cool, I'm right where I want to be. So I come at it from a slightly different perspective. There's a lot of effort I've put into this to make this stuff work that has absolutely nothing to do with fun things like weather and chasing storms. It's not for everyone, but I think I was playing the long game and it paid off. And I hope to share my code with everyone as soon as I can get the time to bundle it up and make it usable. So in other words, if other people are interested in doing this kind of work, I'm going to try to make it. It's one of my goals is to try to sort of nudge the community towards maybe considering doing higher resolution simulations just basically for basic research. So I began working on this particular problem in 2010. I went on my first sabbatical when I was in Central Michigan at NCAR, which is wonderful. And I was working with George Bryan, Rich Rotuno, and during that time there, I started to experiment with the Bluewater supercomputer was just coming online, and I was trying to figure out ways to write. I wanted to change the way the model wrote data to disk, which sounds horribly boring, but it had to be done because I needed to stream data to disk very fast. I have a method that I developed that allows me to save data every model time step, and it only takes like 3/4 of the model I/O time or of the model time. Now, if I save data every 1 second, it might take, say, 30%. So in other words, I'm getting I/O to be not a big deal. And if you ever run on supercomputers, if you just continually add more cores, chances are you're going to run into the I/O bottleneck when you start to save data because most models aren't written well to save data on parallel computers. So anyway, I got the process working. Then I was like, I'm running out of computer time and I don't have a tornado yet. So I have this wonderful environment to simulate stuff in and to create the data, but I don't have the storm I want. Lou Wicker, through my connection with Robert Wilhelmsen, said, here, Lee, try this sounding. Be careful, it might break the machine. Those were his exact words. And when I ran it at 250 meters, I got this screaming little mesocyclone. I thought, this is good. Then I ran it at 100 meters, and then I'm like, ran it at 30 meters, and I adjusted the box, and sure enough, I got the thin blue line that was the tornado, and it was very exciting. And we continue to explore this storm as well as other storms we're beginning to simulate as well. So, yeah, I've already kind of gone over this. We've had success down to 15 meters, 20 billion grid zones. I have a simulation right now as we speak on Blue Waters, running about 80% of the machine, 627 2,200 cores, 250 billion grid zones. The thing with when you run a job that big, node failures happen frequently. So one of the nodes just dies. So it's like, oh well, start the model over again. I have a script that starts it up again. It's kind of a pain, but you run into all sorts of fun issues when you're running at this scale. Okay, so the real storm, I'm not going to talk too much about the real storm. It's been written about enough to say that it did produce a long track EF5, as did our simulation. That's good. That means our simulation is probably not completely wrong. However, I discovered early on a very frustrating problem in that I had make a small change to the model set of initial conditions or a small change to a parameter or even recompile the model and try to rerun it and I would get a different result. When I say a different result, sometimes I got a different result in that I did not get an EF5 tornado, which is really infuriating and frustrating because, you know, here you go. You've got a storm, let's rerun the simulation, but let's get it to be centered in the box better or something, and then it doesn't happen. So the lesson here is that there's definitely the Lorentzian problem is still here. If you change the initial conditions or change parameters a little bit, you may get a vast divergence in solution, at least in the details. I mean, I always get a very monster supercell, but I don't always get an EF5 tornado. So anyway, there's a lot of bugaboos in this world. The sensitivity issue is one I'm hoping to turn on its head basically by just running ensemble. So in other words, create a nice spread of initial conditions or whatnot, and instead of worrying about whether it's going to produce a tornado, just run 30 simulations at 30 meters and then do your statistical analysis. And then that will hopefully give us some answers to some of the physical questions. The second storm I'm going to be showing you today is actually taken from the 18Z Jackson Air Force Base, Alabama, RAOB. So you can actually go online to the University of Wyoming and download that sounding and put it into CM1 and get a tornado. It produces a long track EF4 5 strength tornado. So we're calling this Tuscaloosa, even though it's not. We're not saying we're doing the Tuscaloosa storm, but it was certainly the air or the sounding is representative of the air from that outbreak. We see the streamwise vorticity current thing that I'll show you soon that we sort of identified in our first simulation in this storm, which was good, but it doesn't have to be there. It isn't like in place like it is for the El Reno storm. It's a different morphology, but there's one there. There's a point in the simulation where the tornado is just churning along and there's a surge in the forward flank and then the SVC sort of rises out of the ashes. It's actually kind of cool. So there is definitely some push-pull going on between downdrafts in the forward flank and the tornado strength. So I'm looking more to the forward flank of the storm because that's where I see most of the interesting things. A little bit of history. That one in the top left, you know, I think of that, and I'm sorry if I forgot anyone, but Bob Wilhelmsen and his study of a severe storm, which actually earned a Grammy nomination. One of his students, Bruce Lee, worked on the connection machine, CM5 machine, and did his work on non-supercell tornadogenesis. Ming Shui's work, where he commandeered the Pittsburgh Computing Center for like a week or something, and he got Del City to produce an EF5 tornado. There's similar work with ARPS done by Noda and Nino in 2005. There's our work, and then there's a recent paper in a Chinese journal or a Chinese scientist that they duplicated my set of conditions to study an EF4 strength tornado that occurred in China. So one thing that's interesting about this is not an AMS journal, so we have to always keep our eyes out on all the journals. I use Google Scholar to alert me with keywords, so I'm not missing any important stuff. I think sometimes, you know, we get in our little silos of our journals. I think it's important that's just my little commentary there. But anyway, so I was like happy to discover that someone else is doing this as well. I think they're at 20 meters or something. So okay, enough of the background stuff. I'm not an observational meteorologist personally. I collaborate with them, and I'm always really sensitive to the issue that I'm a modeler and that I want to make sure that my model is not out in model land. So I like to compare to observations. So here's a nice supercell picture Roger Hill took. It's nothing, I'm not saying anything specific about this storm other than it has some nice features that you can identify. You see this nice wedge tornado. You see the rear flank of the storm. We've got the forward flank of the storm. We got this nice tail cloud. You can see the rain coming down over here in the forward rain and hail. It looks like a classic, tasty looking supercell. This tail cloud's interesting, and one of the reasons we use this figure is because it sort of implies some of the flow we're seeing in our simulation. You sort of see this thing, the SVC, which is typically behind it, but it's sort of like this flow and feeding into the updraft is something that is similar to what we're seeing in our simulation data as well. This is my similar view, so to speak, of the storm I simulated. I'm red-green colorblind, by the way. I thought this would look good. It looks kind of weird, like you're floating in lime jello, but I made the sky blue and the ground green, and this is what you get. But I didn't do the hydrometeor fields. This is just the cloud field, but whoops. But you can see the same things are there, right? It looks like a supercell. You wouldn't be fooled that it's a real one, but at least all the parts seem to be where they're supposed to be. So this is just a sequence that just goes over and over again, just to, again, get you habituated with the idea. It's a loop, meso, rear flank, forward flank, tail cloud, and I'm gonna be focusing a lot of my time in this region of our simulated storms. So this is kind of what we're looking at. So this long sequence is our 30-meter control run. This is of the 24 May 2011 storm. So this is the cloud. I'm painting the surface with theta rho prime, which is a proxy for surface buoyancy. Blue is cold, clouds, and rain and hail. So keep an eye on, you know where it's going to form, but notice all this activity. You see these little sort of appear to be little vortices or something hinting to rotation, kind of streaming in from the right. At the same time, you're starting to see these sporadic downdrafts in the rear flank. But the tornado just kind of seems to form out of, I don't know what, it just forms, kind of like sort of what you see in the real atmosphere. And this goes on for a while. I do speed it up at some point for the sake of time, but the morphological characteristics of the tornado are interesting. It undergoes some weirdness as it transitions from a single cell to a two-cell tornado. Here you see these RFD surges, blast, 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 these really hot, but theta rho prime is positive, and yet there's rain. It's as if these downdrafts, I'm pretty sure they're dynamically forced. They're actually pushing the rain to the ground rather than the rain falling to the ground. I mean, the adiabatically compressed air hits the ground before the rain does. So Dan and I were talking about this earlier. I think a lot of the RFD downdrafts are really dynamically forced, which is, I think, an important thing. There's a little vortex that just kind of comes around. So you see this kind of detail. You won't get this kind of detail at 100 meters, 500 meters. You really need, and again, saving data frequently lets you see all these transient things that I think are important. So the thing is transitioned into a wedge. Now it's a rain-wrapped wedge. It does the normal things. In this sequence, I'm looking at what's called I'm just looking at vorticity magnitude. I'm shading the vorticity magnitude. I'm just calculating vorticity, square root of the three terms, square root of the three terms. But I'm shading it by the vertical component. That means when you see a vertically oriented vortex that's blue, it's anticyclonic. This is cyclonic, okay? And what you'll see is there's blue guys and red guys everywhere in supercells. So the rear flank is over here and the forward flank. So I'm kind of looking at it from the cold pool side, or the whatever flank it is in between. So first of all, there's no tornado yet. But look at how much of the meso is just cold pool air. This is just cold pool air being slurped right up. I mean, if you look at the mesocyclone, the core of it is all cold pool, and the outside of that core tends to be the cape air, the moist air that's supporting it. There's interesting things going on. So the SVC, and we have formally identified it as like this helically flowing air that forms. It's basically easy to show on here. So this is air that's streamwise vorticity. So it's vorticity magnitude, but it's streamwise in that the wind vector and the vorticity vector are aligned, so the flow is helical. So we think this thing here, this bundle of vorticity, there's things going on that's helping to drop the pressure, to help to strengthen the low-level updraft and the updraft at higher levels as well, but it's providing that intense stretching needed to maintain the tornado. So the thing I like about our theory, or this feature, is that it doesn't require a trigger. It just basically, it's like you're putting your foot on the accelerator pedal, and you're just pushing and pushing and pushing. And there's abundant vorticity in the simulation. So this is why we call it helically flow, or you can see that it's streamwise, right? Because the vorticity is sort of, it's moving in the direction of the flow. It's not entirely streamwise, but it's very much very much in that regime. So our theory is basically that this is important. What's over here in the forward flank is important. These little vortices here, you can think of them as, this is kind of like a vertical vortex sheet. It's not, sometimes we get negative sign vortices, so it can't be a true shear instability, but it's the structure here is fascinating. And this is where we're focusing much of our research. I finally got an NSF grant to actually do the analysis of this data, and I have a graduate student who started working on it in earnest last month. So it's taken a while, but in my world, you get the computer time first, okay? Do the simulations. You got to do them. Use the time when you have it, and then park the data and then analyze it later. That's kind of what I had to do. So here's an example of me saving data every model time step. So you're seeing every 1/6 of a second in this little sequence. So we're looking towards the north. This is, you're going to see these are horizontally oriented tubes. So if they're gray, that's why they're not shaded, because they're horizontal. And then I've actually shaded these by the vertical magnitude of the updraft. So strong updraft is green, white is a little weaker, red's a little weaker, but you can sort of see the progression of the updraft strength painted onto the vorticity magnitude. So watch these guys, look at this. This is a horizontal vortex that over the course of 1 kilometer has been tilted entirely into the vertical. That's pretty intense. I mean, that's some serious vortex tilting, and you're gonna assume stretching along the path of that vortex. And yes, there is a bunch of horizontal stretching of horizontal vorticity in the cold pool as well, and that only makes sense. If you've got this giant updraft pulling, slurping air from all directions, air is going to accelerate as it comes into the bottom of the updraft, and if it's accelerating and it's helically flowing, it's being stretched. I mean, there's just no way it's not, and it is. We've calculated it. I don't think vorticity is necessarily going to be the solution to this problem, or doing vorticity analysis, but we're doing that at least as part of our due diligence. So here's the SVC sort of making its way up and around behind. And this side, I'm shading it by the 3-dimensional wind speed. It doesn't really matter. Now watch, all of a sudden, notice how everything looks kind of linear. I mean, everything just sort of looks like sharp. This is when you have this big drop in the pressure aloft, like sort of a kilometer or two. It's like suddenly, we're stretching everything. And before long, it's just this accumulation of vorticity. We say, okay, we have a tornado now. I mean, there's no more data in here. I can't remember at what point I'll speed it up here. It becomes a tornado, but there's tornado genesis. That was it in our 24 May simulation at 30 meters. And it still ends up, building up more and more vorticity. And it gets stronger and stronger. Here's a different view of the same thing, but just watch as suddenly, all of a sudden, you see all these vortices just kind of come together. I think what's happening is, and I have another sequence that shows this better, there's this sort of parade of vortices that moves from the forward flank to the rear flank, in a storm relative motion. And look at everything just kind of goes, hello. I mean, everything's converging, literally converging. I mean, because there's this giant black hole of, this giant lack of low pressure, okay? It's just, so this is why I'm looking at this from a different perspective. I'm thinking that this thing here has a dynamic response to the pressure field, which in turn affects the updraft field, which in turn, because everything is about the updraft, in my opinion. I think we spend a lot of time looking at precipitation and downdrafts because we can. We can measure those things, or we can imply downdrafts based upon the horizontal winds when they hit the ground, but if there's any way for us to measure updrafts better directly, that's what I'd like to see in our field. If there's a way to directly measure updrafts, because that's where the action is. So here's a similar thing with the cloud base thrown in there just so you can see it. Now the tornado's on the ground. It's now a tornado strength tornado, whatever that means. And it's not just a vortex. And you'll see, lots of stuff coming in from the forward flank. Stuff that comes in from the rear flank, if you actually travel its origin, sometimes it makes a little trip around, so it spends a little time in the rear flank, but it's really originating from the forward flank. There's almost like there's a wall of inertia that the rear flank just can't get in there. Okay, so there was recently an article in Science News, or Jana Hauser's work. She's an OU grad who is at Ohio University, and she's an observational meteorologist. She's one of Howie Bluestein's students. She has a theory that the 31 May 2013 storm, the one that killed Tim Samaras and those chase partners, that storm, the tornado, actually formed from the bottom up. Okay, so there's this idea that there's a bottom-up mechanism of tornado genesis, and there's a top-down theory of tornado genesis. So I'm like, okay, Jana, I'm going to go back. I hadn't really done this before, so all I'm doing here is I'm shading the vorticity magnitude isosurface of 0.5 inverse seconds, which sounds really big, but at 30 meters, you're going to have large vorticity values. I'm shading it by the storm relative horizontal wind. So if it's a tornado, it should be bright and erect. If it's not a tornado, there might be some vorticity, but like this is almost transparent. So this is like, the winds aren't very strong, so it's not a tornado. So I'll run this through once, pose this question, and I'll run it through again slower and see if we can get any insight on this. So we don't have a tornado yet, and then we'll let it run, and then I'll pause and we'll do it again. Okay, there's tornado genesis. So, all right. We saw a vortex originating near the ground. It sort of became a taller vortex, but it wasn't a tornado. Tornado strength winds formed aloft, and then not a tornado. Okay, it's not a tornado because it's not tornado strength winds in the ground. That's my definition. It's not a tornado. It's still not a tornado. Still not a tornado. We have tornado strength winds aloft. So here's an interesting thing. Is that a tornado? No, because we don't have tornado strength winds in the ground. Now we have a tornado on the ground. So is it a top-down process or a bottom-up process? It's sort of a little of both, at least looked within this context. This is not meant to be the final anything. I just did it, thought it was interesting. You typically have your vortex stretching, your seed vortex starting near the ground where you have the strongest amount of stretching. I'll show you DWDZ in a second. So your vortex may originate near the ground, but does the tornado, you know what I mean? Is it a top-down? It depends on what you're really asking. You have to ask that question better because I don't know how to answer it. But this is cool. This is some stuff that Kelton Albert just did. So he's doing his PhD work on this simulation or this work. This little box here, we're gonna do horizontal averages over that area for each level in like a cube going up, 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 up. And everything you're going to see in the next slides are horizontally averaged over this region, which is pretty much centered right on the updraft. You have the low-level updraft. So I'm just going to show you DWDZ. This is the stretching term. You can think of this as proportional to how much stretching you can do for a tornado. So the color map, goes to yellow is large values. First of all, notice that the biggest values of DWDZ are near the ground, but let me zoom in a little bit so you can see this a little better. So this is 1 kilometer. So we have 33 grid points because with 30-meter grid spacing. But just look at this. DWDZ is the strongest. The stretching is the strongest here. It's strongest here. It's even lower. You get the strongest stretching even right at the ground. Tornado. That's the tornado. That's kind of interesting. So, and that's averaged. Okay, we're averaging things. So this isn't just one little vortex. We're actually looking at like averages over a surface. So intense stretching near the ground right prior to tornado genesis. Shouldn't be too much of a surprise, I suppose, but what it tells me is it's about the updraft. It's about the updraft. It's about the updraft. It's not about the downdraft. Okay, in this sequence, watch this sort of parade of vortices. This is 20 minutes before the tornado. Again, we've got plentiful vertical vorticity in this supercell long before there's a tornado. Yeah, some of it's anticyclonic. Occasionally we get anticyclonic tornadoes, but there's plenty of it. We don't need a proximate downdraft to bring it down to the ground because it's already there. Downdrafts, way the flip over here, did that work 20 minutes ago, and the storm is moving over that air. That vorticity didn't go away. The cold pool is full of it. Anyway, let me just watch this. Watch this parade. So everybody just keeps going rearward, rearward, rearward. Watch. Look at that nice juicy red vortex. Well, it's just going to keep going. Look at that one. It's going to keep going. Keeping going, keeping going. Now the SVC is starting to really take off. Notice things kind of slow down a little bit, and when you see the one that doesn't keep going and it kind of wraps around, there's your tornado. I didn't see a trigger. I didn't see anything that it's just like a steady process. It's a cumulative process. Partly you've got these vortices that help I'll speed it up for the sake of time. Once it's anchored in place, yes, we need to, got a nice SVC going here. The updraft is very strong. I'll show you that in a moment. There's one of those anticyclonic vortices that gets sort of advected around the tornado core. You see that kind of stuff. There's a good blast of air from the rear flank that starts kicking up horizontal vorticity. You'll see horizontal vortices grow almost out of the ground and be tilted and stretched. It's really fascinating. Now it's a 2-cell tornado. It's just going crazy. This is when you might even get some multiple vortex action in 30 meters. You need to go a little higher resolution to get that right, but the tornado just goes and goes and goes. It's really quite fascinating and fun to watch. Here is the same 1/6 second data, well into maintenance, just to show you this in as much detail as I can. Beautiful examples of how it's peeling. The updraft is peeling vorticity right out of the cold pool at the lowest levels, under 100 meters. And it's able to pull it up, slurp it up, tilt it, and bring it into the wonderful world of cyclonic rotation. The SVC is kind of off on the side, doing its thing, which I think is to strengthen the updraft. But when you have an updraft that's that strong, it's just going to do all sorts of cool things. I mean, I'm interested in what's maintaining that strong updraft more than I am interested in the implications of it, namely this screaming tornado. We'll get to that. But right now, I'm just fascinated by the fact that this can actually happen. And we're starting to get an idea of what it takes to maintain a long track tornado for a long time. But this is all beautiful. I just love this. This is the same stuff we see in the chamber models. And we're doing a full cloud model simulation. So this is one of my simulations at 15 meters, I believe. So the solution we get as we go to higher resolution tends to be similar, but different, as you'd expect. This is actually an anticyclonic tornado. One of the things that plagued me with this simulation early on was I kept getting this anticyclonic tornado. Now, why is that a problem? Because I'm a nobody who wants to publish work on supercells, and if my first paper is about an anticyclonic EF4, no, it's not going to happen. It's because those are so rare. There's only one that I know of that's ever happened. So I'm thinking something's wrong with me, the model, I don't know what. But you know what? Anticyclonic tornadoes happen. They do happen. This is in the spot where you'd expect it to be, et cetera, et cetera. But anyway, let me just run this and I won't complain about all my problems too much. So the anticyclonic tornado kind of dissipates and the cyclonic tornado forms. And now you'll notice the tail cloud is much more cellular now. Not all tail clouds look that way. Some of them look pretty laminar, but that's one pretty obvious difference. I'm also using a TKE scheme here as opposed to Smagorinsky in the other simulation. You ask me why? Because it worked, that's why. I'm telling you, when I put on TKE, I didn't get a tornado. And this is the problem, understanding these sensitivities. Look at these boundaries.
So this is Smagorinsky?
This is TKE. So this is TKE and 15 meters. But you know what? This is like a 4 or 5K boundary in the temperature, theta rho prime. So that's a boundary. It's not in the rear flank. It's not in the forward flank. It's sort of in the middle flank, or I don't know what flank. But my point is all this fascinating turbulence and inhomogeneity in the cold pool. We need to focus on that, and that's one of the things we're doing. But this one's kind of a fun simulation because it does that. And again, it dances around a little bit. I look at this stuff and I don't know what's going on. But I think it's interesting, and there's interesting things going on. I'll show you the vorticity field. So there's your anticyclonic tornado in blue. Watch it dissipate. And then there's sort of like our cyclonic tornado in red. Watch it grow. Onward and upward. Everything goes up when you're around a updraft. I'll slow it down and zoom in again. So here's tornado genesis, or tornado decay of the anti. And you'll sort of see stuff kind of making around the bend here. Yeah, there's certainly some air from the rear flank that's coming in, but I don't really think that has too much going on. There's the tornado, and it just goes from there. It's really quite. When you get to this resolution, it's like fully formed turbulence. It gets a bit nasty. That's when you start having to do things like temporal averaging and things like that, which I will show you in a moment. Here's another view. There's that beautiful the helical flow of what I'm calling the SVC, and now it's phosphorescent spaghetti, but it's still overall an SVC-like thing, right? You see the overall rotation and the tilting. And it is contributing towards the pressure drop, et cetera. Okay, excuse me. Speaking of pressure drop, so going back to the 30-meter simulation, I decided to do temporal averaging. I want to take out the trees and just look at the forest. So because I've run the simulation so many times, I know exactly the box speed to set it. So the storm pretty much sits right in the center of the model domain for almost the whole simulation. Luckily, the storm isn't cycling and bouncing around. It's a pretty steady thing, so I have that luxury. So all I have to do is average in time. Each one of these frames you'll see is 121 averaged times, 1 second intervals, centered moving window. So every calculation has 121 times in it, averaged over 2 minutes, centered in the middle. So there's a lot of times in these things. So this helps to really smooth things out. This is the pressure field, pressure perturbation field. The first contour is minus 15 hectopascals. Here's the updraft. So you see what I'm trying to do here, right? So I'll just let it go. So this is why I'm thinking the pressure field might be important. So look at the time. It's like 2 minutes, 3 minutes has gone by, 4 minutes has gone by, 5 minutes has gone by. Now we're entering into 20 HPA, 25 HPA. So that's probably important. Notice the updraft is not only getting stronger, but it's kind of, you can see that it's lowering to the ground, or you're getting strong velocities near the ground. Now we're entering the 25 HPA contour. Tornado comes off of there. You can sort of, because this is temporally average, don't take that whole morphology too seriously, but you can kind of see what I'm getting at here, right? Also, this little nub here is associated with the SVC. Associated with, meaning we haven't quite figured out causality, but it's definitely associated with it. And you see also the storm the tornado gets a little, it doesn't go straight into a super destroying wedge mode. It takes some time for that to happen. But when it does, you'll just see these ridiculous pressure drops. And you'll see, look at the updraft, look what it's doing. The second contour is 40 meters per second. This is like, I don't know, a couple hundred meters above the ground. It's just ridiculous. And again, look at this strong DWDZ. It's right where this pressure thing is. I'm thinking non-hydrostatic vertical pressure gradient is probably controlling or modulating that updraft. And that updraft can sort of help the tornado live. Because we really still don't understand how tornadoes are maintained. What's the tornado is embedded, it's enfolded into the updraft, it's ensconced in the updraft, it's along these very strong horizontal shear of the vertical wind. It's all, without an updraft, you don't get that. So that's why I want to look at that. 1, 2, 3, it's 50 meters per second. Of course, in a two-cell tornado, you'll expect to have a downdraft in the center as well. This is another view of the same thing, only I'm using volume rendering, and I'm including streamwise vorticity only over a certain threshold. So again, pressure drops, start spreading out. So this is a region of low pressure that's expanding. You can see the updraft, the intensification of the updraft. You can see how this is again, temporally average data. So I've taken out most of this is like the base, if you want to even think of it, it's like the steady state part-ish, and there's a tornado, gobs of streamwise vorticity, strong updraft. So there's definitely something going on between these three things. And essentially, it's like getting the causation and figuring out all that detail.
Did you get a downdraft in the core?
Yeah. Oh, yeah. I get a two-cell tornado. 40 meters per second, 50 meters per second. It's pretty strong. At 30 meters, we don't quite get it right. At the higher resolution, you start to see it even better. But yeah, we get a two-cell. We get a multiple vortex. We get all kinds of tornadoes. It starts out as a single cell and it converts over to a two-cell. Here I'm shading the streamwise vorticity by the storm relative wind speed. So I'm wanting to look at the stretching of streamwise vorticity. So where you see this streamwise vorticity start to get more of this color, that means it's the wind's stronger along that. So I like shading one thing by another. So you can see all this streamwise vorticity coming in. And you can see that the speed is pretty strong. So, how can you not stretch something, right? It's going faster. It's accelerating along its helical axis. So that's another way to look at this. I'm just trying all these different techniques to sort of understand, get a story going before we really dive into the quantitative stuff, which finally we have funding to do.
If you etched in the surface boundary, where would that be?
You're talking about like the cold pool.
Between the downdraft and the inflow.
Yeah, from this view, this is the rear flank, so it's over there. Sort of, we're looking at it from the east, looking west. So, yeah, it's on the other side there. I'm not showing the cold air in this one. I'm just showing the vorticity. Here's another way of looking at this. So here is prior to tornado genesis. This is the pressure in red. These are temporally averaged, and I'm going to show you the wind field. So here you can see, here's the cold pool, right? Again, this is all temporally averaged. I'm going to show you, I'm now shading these vectors. So now we're sort of normal to the SVC here. And I'm going to show you tornado genesis occurring in temporally averaged data, but just looking at the wind vectors. Again, temporally averaged. So you see the wind vectors will just get longer and longer and longer as the updraft gets stronger and stronger and the tornado forms. So I'm looking for anything transient, I'm looking for triggers and all that stuff, but I'm not seeing it. Granted, I'm temporally averaging, and then the SVC takes off, you get 70 meter per second winds, just 400 meters above the ground. It's ridiculous. Zoom in here again. Watch those vectors get longer, stretching, DWDZ, DWDZ, and then the tornado eventually falls out of that. So again, this makes it, I'm thinking in terms of storm-wide processes. What's producing this? One more time, zooming into the ground. Look at these just more intense stretching. and there's your tornado. What else we got here? I know I've got more stuff. Okay, so I am actually interested in the real atmosphere. This happened not too long ago. The reason I show this one, I pulled this off of YouTube. I give the guy credit, but I can't remember his name. Nice horizontal. So this is an EF3, I think. The reason I show this is that it came very close to Paducah radar, and interestingly enough, so one of my students, Austin Dixon, he is doing his master's degree. He's looking at like what the SVC would look like on radar. So he built a radar emulator, and this is I'm sorry I don't have the actual values here, but this signature, I actually have a pointer I could use. So this signature is basically it's a jet, or think of it as a jet. Storm relative air is flowing in, and the tornadoes right there. I said, hey, Austin, put the radar where Paducah would be for our storm, and we get a very similar signal. Now, I'm not saying this is the SVC or anything, but we still get, this is basically a inward motion. It just looks similar, and we thought that was interesting. Dan, you had, yeah?
It's still inbound of the radar, but you're saying the storm relative it's moving towards the radar.
Yes, yes. In other words, well, I'm basically saying,
it truly is outbound on the simulation.
I think in this case, I'm trying to remember. All I know, I'm not good with colors and stuff, but these signatures both indicate a similar flow regime.
Yeah.
So in both cases, it's storm relative inflow. So let's just call it that. Ground relative, yeah, and don't take the colors too seriously. But the only thing to really take away from this is that, wow, this is the thing that's important to me, because this may be something, because we were so close to the radar, it's a C-band radar, et cetera, but maybe, we're looking for the real stuff. But Austin's working on that problem. So I didn't want to be a one-trick pony. I didn't want to have one storm that I've only been able to do. So our team has been looking for other environments to try. And Kathy Finley at the University of North Dakota, recently at St. Louis University, she found that this 18Z Jackson, Mississippi RAYOB, she did tweak I think she tweaked the boundary layer just a tiny bit to keep the Richardson numbers, just to stabilize it a little bit. But nothing, you don't even have to do that. And it produces a very photogenic, if you would let me use that word for a model simulation, storm. One of the issues we have with this particular simulation involves hydrometeors not being properly centrifuged from the tornado. That means our condensation funnel kind of goes away. It gets eaten by rain or something, so we don't have a very nice condensation funnel in this storm. And that's a problem we need to, I know how to do it, it's just a pain in the butt. I don't want to have to add some code to the model to handle centrifuging. So looks pretty good. You get, nice tail cloud, beautiful cascade of rain and hail here, a little rain foot showing you this. Well, I call it a rain foot. It's really indicative of that inflow. Here's another view of this storm during tornado genesis, the vorticity field. So I know there's a lot of information on here. This one, what's interesting about this storm is it's actually pulling vorticity out of the environment ahead of it. I think there's vortex sheets that are sort of folding up into actual vortices. Really interesting, but this is environmental vorticity, not from the cold pool. So this is where the SVC is, or there's one of those little things that looks like an SVC. Again, I'm not trying to just find an SVC everywhere, but this is pretty SVC-like. And there's your tornado, so everything's kind of where you'd expect it to be based upon our 24 maze simulation. Here's another view. Just amazing, beautiful, cascading forward flank blobs of precipitation, total chaos or turbulence. There's our tornado down here. And over here, you'll see there's a surge at one point in time, there's a surge in the forward flank, and you sort of see the SVC vorticity kind of grow out of the ground. But I guess the important thing from my own perspective is we didn't just do this with one storm. Again, Kathy's going to be doing the analysis on this one. This is about a minute prior to tornado genesis, so you have a nice hook. You have a few different vortices, and I'm sorry I clipped out the rear flank. It's not because I don't like the rear flank. It's just that's the way this image turned out. But just watch genesis here. It's just kind of like, everybody come on together and let's form a vortex. That's, and so I'm thinking updraft. I'm thinking convergence and stretching. Here's the same tornado genesis, so there's downdrafts in the rear flank. Now here's the perspective, okay? So this is just about tornado genesis. This is reflectivity, there's vorticity, and the updraft. So these are the same thing, so there's the proximity. So it's kind of hard to always see, but let this go. Little vortices getting stretched. This little guy here, this is a different morphology than 24 May in that you really start out, it takes a long time to ramp up. But I mean, that's a tornado, and it's gonna do its thing for a long time. And it just kind of happens. You know, I didn't see any trigger. I didn't go back far enough. That's one thing with the simulation. We have to go back even further to see what set that up. But here's another example of tornadogenesis for that storm. And you know, just kind of focusing on the updraft structure. You can see, I'll speed it up because it'll take me all day if I don't. And it's just, there's when it's sort of transitioning over to a 2-cell. You can see these transient downdrafts. It's kind of trying to do its thing. The tornadoes, they're dynamic things. They often do funny things that I don't understand. And there is the 2-cell. You can see the barber pole thing, and now the updraft's super strong, you know, to the ground. And I'm going really fast because it eventually gets occluded and goes off stage, exit stage, right? Goodbye, tornado, thank you, come again. All right. So for the last 15 minutes or so, I'd like to sort of, I've been partnering with a videographer, storm chaser by the name of Hank Shima. He's Pecos Hank on YouTube. If you've looked for really good footage on YouTube for tornadoes, you've probably come across his channel. He's a really nice guy. He contacted me and I was like, let's take some of your footage and my models and put them side by side and see if anything looks good. So I do this fun slide where I compare. This is our simulated storm rendered by David Bach at NCSA, but we'll just kind of come up here and kind of look at, you know, billowing cumulus clouds. That looks pretty good. I mean, yeah, that's definitely a model, but you know, that looks all right. I wouldn't throw it out of bed or whatnot. It's looking all right. Mammatus clouds looking really good. You'd almost be forgiven for thinking the left was fake, but it's.
The first simulation I've seen that shows mammatus.
Yeah.
That's pretty impressive.
Yeah. Tail cloud, about in the right place, looking like you know, that's, and again, I forget if that's storm tornado or not, but he went through his catalog and did this, so it was kind of fun. Even this sort of SVC-like flow along the forward flank, some similar things there, which is kind of encouraging because that's probably the most, you know, if anything, the SVC is what we're hanging a lot of our hat on. There's just kind of just kind of comparing. I mean, it looks pretty good. Again, you wouldn't mistake one for the other, but I'd say that we're definitely getting some things right, and that's important. Here's a nice multiple vortex. You can actually see them. I'll sort of step through here. I mean, there they are, man. That's the cloud field. That's just the cloud field. That's amazing to me.
What's
I mean,
the largest number you've ever simulated?
the largest number?
Of multiples.
That's a good question. There's like 4 or 5, 6. Yeah, I haven't picked through every frame, but you can see right there one, and it just looks so right. Yeah, I'm not entirely sure. And here's the Katy tornado, and showing some of those nice little horizontal guys, and you see sort of similar weirdness going on in my simulation. So again, I'm very cognizant of the fact that I'm a modeler, but I'm very, very much trying to keep my eyes on the real world because we need to do that. Okay, so as I sort of round things up, I'll sort of conclude with some ideas, some thoughts. I think some of our conceptual models for supercells and supercell tornadoes need some revision and rethinking. Those of you familiar with the more common theories of tornadogenesis, you know, you think about RFDs and things like that. I'm not seeing that in my simulations. I'm just not seeing it at all. So I think we need a new way of looking at this. I see tornadogenesis almost as an artifact of a storm-wise intensification process that occurs in the lowest couple of kilometers of the mesocyclone. That it requires, I mean, again, we have to connect all the dots here, but it requires the updraft to really get intense at low levels. And what I'm seeing is there's an abundance of existing vertical vorticity in these simulations, and I call it a vortex of opportunity for lack of a better name, but one of those guys is there to be stretched, and you see it in the simulations. The tornado results from one of those. This pressure drop that we're seeing seems to slow things down in that parade, and then everything just starts to accumulate in one spot, and the tornado forms. So I don't know, tornadogenesis could be bottom up, top down, and side by side as well. It seems like, you know, if you're really interested in that question, it seems to be a lot of things, but I think maybe we're asking the wrong question. We're focusing too much on the tornado and not enough on the environment that supports it, kind of. But that's just my, you know, don't bring a modeler to an observation fight, right? Anyway, so that's kind of my talk. I definitely want to acknowledge all my collaborators on this project and the National Science Foundation for supporting the Blue Waters project, for partly supporting my own work and that of my graduate students. Kathy Finley and Bruce Lee and I have been working on this for quite a while. We've been sort of formed a research team a few years ago with Bob Wilhelmsen as well, who's now retired. I'm doing work with Larry Frank at UCSD. He's a guy who's a physicist who does work with brain MRI scans, functional MRI scans. We're actually going to try to use his entropy field decomposition technique that he uses on brain scans on Doppler data. It's crazy. It's one of those NSF, what's it called? The weird NSF one where you just take two completely different fields and smush them together. And Dr. Morgan O'Neill, she just started at Stanford. We're doing above anvil cirrus plume modeling. So I'm going to expand my modeling into the upper troposphere, lower stratosphere. And I have them with me. I could show you later, but I have some. I reproduced Holmeyer et al.'s paper at 50 meters isotropic and got a lovely above anvil cirrus plume, and I'll be looking at those as well. So anyway, I think I'll stop. I'm glad my voice held up. I've had this cold, but it seems like I made it, so I'm happy. So I'll just shut up and take questions.
Hi. Very interesting. I'm blown away by those simulations, the animations.
No pun intended.
I'm curious, though. You started off your talk mentioning that you have some sensitivity to initial conditions, so there are often simulations that don't generate tornadoes. But you showed mostly successful
of course.
genesis.
We do that all the time in science. How many of you doing numerical models, what percentage of the simulations that you actually present to the world, it's like 0.2%, right? You've got like 700 shitty simulations that you don't want to tell anyone about. No, I'm serious. Now, I know what you're getting at. The truth is, I'm more interested in the sensitivity problem than almost anything else. But first, let's do some phenomenology, okay? There's enough low-hanging fruit here for us to pluck before we start worrying about Lorentz and his butterflies. But that's a real problem.
It's not so much the sensitivity of initial conditions per se, but in the storms that don't generate tornadoes, do you see some of the salient processes?
I don't see.
Yeah.
We're just beginning to do that because I've spent so much time trying to create the good simulation. It's easy for me to create the ones that don't go. I can just tweak a few knobs. So I have a couple of what I call failure cases on disk that are being looked at by one of my students because that is totally how we're going to get to the heart of this. What's going on? It's the same environment. It's the same environment. That's really amazing. Oh God, we have a EF5 versus nothing. I mean, that makes my brain want to explode. That's why I think in one way we need to just do ensembles to sort of upfront acknowledge the fact that there's sensitivity, so let's do an ensemble. But still, we can still do single deterministic runs, I think, just to understand the internal workings. So we're just mostly on that part yet, but I totally agree with what you're getting at about the sensitivity issue. Dan, you do the...
Sure, yeah, related actually. Have you ever thought about taking your simulation when you get the tornado, stopping it and doing tests where you perturb something in it?
Yep.
And have you done that then?
Nope, but I've thought about it. No, what I've thought about doing is putting RFD surges, but try to get a tornado to form by the, start putting RFD surges in. See if I can get a tornado to form. No, seriously.
The opposite is how easily can you kill your tornado?
Oh, they're hard to kill.
Oh, okay.
The way they typically die is when they get occluded, and interestingly enough, the cold pool gets too warm. I actually see the storm dissipate when the cold pool starts to get too warm. So it's like, but isn't warm air easier to lift? Well, I think the horizontal gradient of buoyancy that's helping to generate all this vorticity, you cut off the SVC or cut off the streamwise ingestion or whatnot, and then it fizzles out. So, I have a zillion ideas. I need 48 grad students is what I need. But that's another.
I just wonder if that's a computationally cheaper way where you would do little restart experiments that you only need to run for 10 minutes.
10 minutes.
If your argument is you're trying to understand what's going on and you visualize it.
Right.
If you could actually do an experiment, you say, maybe this matters. Let me do something to alter that, and then run it for 10 minutes and see how different.
Yeah, no, that's a very valid approach. It's also a tricky one because I've read papers let's turn off evaporative cooling in the microphysics. That never happens ever. So how do you interpret it, right? So some of these weird ass things I'd be injecting in here, I would have to defend them very carefully and say, all right, you understand that. But no, that is an approach that try to kill it, try to form it, try to, rinse, lather, repeat, I don't know, whatever you can do.
Okay. Questions?
Sorry to keep on the initial conditions thing, but sort of merging those two thoughts there. So my background is not in meteorology or any of this, but computationally I'm very comfortable with everything that you've been talking about here. how much of that sensitivity to initial conditions can be accounted for by the fact that, right, when we're talking about having a box of boxes and trying to calculate interactings in between them,
Yep.
a lot of times when you're doing modeling, you have to go way far out,
Yep.
right? And your resolution just falls off and falls off and falls off. Your box, like you said, oh, we'll have the box, we'll try to center it, and then the tornado's gone. Like, what happened? Right, everything that you've said sort of convinces me that this is all cumulative things, like things build on each other, and you have to start with, it's a little hair trigger that happened, we don't know where it was, but right, this is the parade of those vortices. There was a traffic jam, and one managed to wrap itself around, and now you have a pretzel going on, and everything goes to the tornado, right? But if you're changing where the box is and you're trying to be really restrictive because storage space is expensive, so you don't want to save everything to disk.
It's worse than that, though. It's not just that. I mean, I literally give this storm tons of room to breathe in all my simulations. I've made the box taller and wider. But the reason I've changed the box speed is to keep it as centered as possible so that when I do my averages, when I do my renderings, I don't have to move the camera. You see, so I have a real, a pragmatic reason for doing this. Seriously, I don't have to mess with that crap. So the problem, it's the Lorentzi, remember the Lorentzian work where Lorentz was studying this set of equations, he ran a simulation, got a result, he reran it and got a different result, and it turned out to be a truncation error in the floating point or something. He had the least significant bit. So but we know in these highly nonlinear systems that initial small changes lead to big things. So it's really no surprise that you get different results. What I find really hair-raising is sometimes the different result is tornado or no tornado. Because if you looked at the two supercells on radar from the failure case and the real case, they'd look extremely similar. So it's maybe a timing issue or something, but I don't think
it's either whether it happens or it doesn't happen. That actually sort of seems to make sense to me, having coming away from the outside of this problem. Everything that you just showed, I would actually be it would be almost as disturbing if you had a tornado in both cases, but one was an EF2 as opposed to an EF5, right? Because that's what you showed. It was a thing that happened. And if you change the initial conditions a little bit, it doesn't happen. And if it doesn't happen, then it can't build on.
Right. And what you're saying makes total sense. And the way to really crack that is, again, to put a failure case next to a real case and just put them side by side and see where things start to diverge. Because you're probably just going to, I don't know. Again, we still don't understand tornadoes well enough yet, but to understand why they don't form is even a harder question. So, but I think we're in agreement. I have just recompiling the model after not using it for, or I changed the I/O code, but I have to touch a piece of the code. That means it has to get recompiled. Well, they updated the compiler. I didn't change my compiler options, but there's something in the math library that changed. That's the kind of stuff that drives me bonkers. I cannot reproduce my results. I cannot reproduce them exactly. Okay, this is a problem in computational work like this. We always talk about reproducibility. I'm telling you, you physically cannot reproduce those results unless you build a new supercomputer that's exactly that computer with that operating system, that version of those libraries. So that's why I'm not so worried about reproducibility anymore. I just acknowledge the fact, well, the real atmosphere, you can't do it, so you can't do it in the model either. At lower resolution, it doesn't show up as much because you don't have enough time to see that stuff grow. But I still think the way to grab the bull by the horns is just to acknowledge it up front and then do ensembles, which is do 20 simulations, tweaking little bits of things, and then doing statistical analysis, and then you can really get a handle on what's going on.
Yeah, you almost need another software stack. So you do the simulation, that's a whole software stack right there. And then something I've noticed last year on campus talking with people in this department and others is, well, it's a whole other computational task just to take the data and try to do a simulation or a visualization analysis. You almost need non-human eye tools to make comparisons of that ensemble.
We're actually kind of working on that.
This is where the difference is.
Yes. We're going to be building GPU computers to analyze our data that's done on supercomputers to do things, because I think I'm going to take the brute force approach to this problem, and just like you say, just build an analysis environment. In this case, I wanted to use GPUs because I think we get a really lot of bang for your buck. We just have to, I'm just learning CUDA and all that fun crap. But I've got a student who's better at it than me, which is always a wonderful thing. So yeah, well, anyone else? We could talk forever. I got some more questions. I don't want to dominate.
Well, super talk.
Thank you.
I didn't see much focus on this very surface.
Yes.
At the bottom of
Yep.
your run. And
Yep.
things that you might look for. And I'll throw one out,
Yep.
like the high pressure ring that's around the tornado.
Mhm.
Probably familiar with.
Mhm.
And you know how you wind up with that because the air that's being converged in has to basically sort of like trip the boundary layer to where you can actually spin it up at the surface, literally at the surface.
Right. Literally at the surface. The surface of all models is horrible. I use a surface boundary condition that's called free slip with an asterisk next to it. In other words, it's a flat ground, and we use zero strain surface boundary condition, which is not the same as a zero surface strain gradient surface boundary condition, which is, and this is getting really into the weeds, but the CM1 model has one option for free slip and another option that was introduced later. When I use the new option of free slip, I don't get tornadoes. So I don't want to spend the rest of my life farting around with surface boundary conditions. I know everything matters. I know this stuff matters, but I've got a good storm I want to play with for a while before I try to answer those other problems. We do look at the surface. I look at, you can see the vorticity all over the place, red guys and blue guys, everything. But we acknowledge up front that we're not handling the surface correctly. Nobody's handling the surface correctly in models. That's why I continue to run it higher and higher resolution, because eventually I want to get to like a few meter isotropic, at least in the region, so that I can just turn on no slip and it'll actually evolve the correct way. Because that's really, to get the tornado right, you need no slip.
Your big vorticity feeder band with the rain cool air, and that's the Richard tuned on top we had a year ago.
Mm-hmm.
The RFD is like pushed to the side,
Yeah.
which
Yep.
you did today.
It does the same thing.
And
Yeah.
so what you do in reality, you have vortex feeder bands somewhere in the surface layer, everywhere.
So what's that?
You have vorticity feeder bands
Yes.
everywhere, somewhere.
Yeah,
in the surface.
pretty much. You saw. I mean, I showed it, right? You see those things just coming right in. It's crazy.
And then we can take it to happy hour.
Just the notional aspects that reproducibility is kind of used in different contexts. Like, can people take some data or something and go to another lab and do something?
Right.
And then in the kind of the more computational use of that word reproducible, can you use the exact same code? Can you put it on somebody else's computer?
Get the same solution.
And if you can't, it really, I find that troublesome that that's not. Even though these are highly nonlinear problems and lots of parameters, et cetera, and initial condition sensitivity. But, it's sort of like, okay, how am I going to computationally validate what I have in front of me?
Oh,
and
you
then,
can't.
And then,
Yeah.
how can it be in some sense, in the computational sense of the word, reproducible? And you're kind of going past that a little bit.
Well, I mean, I can only work with what I've got. So essentially, I could go on. We'll talk about this over happy hour or something, but I couldn't have gotten to the point where I am now without having a good simulation. Okay, a simulation that was that looked like a real EF5 tornado storm. So when I started getting weird ass results right away, I was like, well, I can't look at that stuff now. I'm not going to go anywhere with this. I'm not going to convince anyone to give me any money for anything. If I start out with EF4s and anticyclonic and if I start up front saying, holy crap, sensitivity is a huge issue in forecasting, we're never going to get over it, no one's going to give me any funding or whatever. So literally, I just want to first just get my hand. I think it's like a storm chase. Every simulation you do is a unique thing of its own, just like when you go out and try to measure a real storm. You can never go back and reproduce that storm. If I worked really hard, I could probably find some compiler option that made the model run 30 times slower but gave me the same damn result down to the least significant bit. But I don't even care. I think the result that you find troubling, I find extremely interesting and exciting, and I want to pursue that harder and find out what this internal variability stuff is really going on. What are the limits of predictability? What are they? I mean, I'm starting to see that there are limits, so that's another fascinating problem that.
Okay.
All right.
So let's thank our Leigh one more time.
Thank you, guys.